In this lecture, we are going to discuss a method of forecasting called the naive forecast. Before we discuss what the naive forecast is, let's talk about the importance of establishing baselines in machine learning. The purpose of a baseline is to have a relevant point of comparison. To give you an example, suppose that you went to your professor tomorrow and say, "Hey, I just made a great discovery. I built a model using deep learning and I got 99% accuracy." Unfortunately, this statement is meaningless because you don't have the context of a baseline. Your professor might say, "But student, we already know that a simple linear model achieves 100% accuracy." In this case, your model is worse than what currently exists, and furthermore, it's also slower. So how can we make sure that we don't make this mistake? The answer is using a baseline. You'll notice that when you're reading machine learning papers, they often compare their results against the existing state of the art. Now, it's important to realize that you don't have to constantly try to beat the state of the art. In fact, that's kind of antithetical to science because all you're doing is chasing numbers. A good real-life example of that is when students study very hard to memorize their notes so that they can ace their exam without truly understanding the material or how it's applied. When you're chasing only numbers, sometimes it's easy to forget why those numbers matter in the first place. Anyway, to get back to the point, it's not always true that you want to compare to the state of the art. Sometimes, if you just want to test whether or not something is working, for example, as a proof of concept, then the simplest model possible should suffice. In time series analysis, the simplest model possible happens to be the naive forecast. What is the naive forecast? Well, it's just another name for something we've already discussed. That is, to copy the previous known value forward in time. One interesting phenomena that happens in time series analysis is that a lot of bad models end up looking like naive forecasts. When you look at the model predictions from afar, they seem to be pretty close to the true values. But when you zoom in, you can see that they seem pretty close only because they're just copying the previous value, or close to it. A really bad situation is this. Suppose that you fit a model and you say, "Aha, I beat the naive forecast because my accuracy is better than the naive forecast." But of course you have to ask, are you talking about the accuracy on the in-sample data or the out-of-sample data? Note that in machine learning, we often refer to these as the training data and the test data. So I will use these terms interchangeably, just be aware. Well, one common mistake is that people believe, because they got good accuracy on their in-sample data, that the same will be true for their out-of-sample data. And also quite commonly, it turns out that the opposite is true. You might beat the naive forecast on the in-sample data, but on the out-of-sample data, the naive forecast beats you. Why does this happen? It happens when your model overfits to the noise in the training data, but doesn't actually generalize to the true underlying pattern in the time series, if one exists. So that's why it's really important to compare your model to a baseline, such as the naive forecast. It's not good enough to say, "I got 80% classification rate on my train set and 75% on my test set." If some other method achieves 78% on the test set, then your model isn't as good. There's one application I've seen a lot, which I think is a very interesting consequence of the times that we live in. Today, there are marketers everywhere on the internet. The name of the game is SEO, search engine optimization. Everyone is trying to get clicks for their blog or to get people to sign up for their course or whatever. And of course, one of the obvious topics that many beginners care about is stock price prediction. Now, if you're taking this course, then you know better, but let's continue the story. So imagine what happens. You take one of the most popular topics that would appeal to someone who doesn't know about finance, like stock predictions. You take one of the most popular machine learning algorithms that would appeal to someone who may not know a lot about machine learning, but has heard many buzzwords like LSTM. LSTM has been a very popular model for sequence modeling. Then what do? Well, you combine these two. You make a blog post on stock predictions with LSTMs. In fact, many people have done so. It's obviously a very appealing idea. No one would blame you for clicking on an article or buying a course that claimed to be able to do this. I won't name any names, but there are some courses that make the very mistake I'm talking about in this lecture. Maybe you're watching this and you know where you've seen something like this yourself. There is another, even worse mistake that these marketers make, but we'll discuss that later when we talk about forecasting in general for time series models like ARIMA. If you want, you're encouraged to skip over to the forecasting lecture so we can continue this discussion. To get back to the naive forecast, let's recall what we learned about random walks. As you recall, a random walk is where, on every step of a time series, I flip a coin or pick a number from a distribution, and that number is added to my current position in order to go to the next position. If my noise distribution is a zero-centered Gaussian with variance sigma squared, which is not unreasonable, then the best forecast is the naive forecast. I can do no better than predicting the last known value. Another way to think about this is, if you build a model that you think is good, but it cannot beat the naive forecast, then it might suggest that your model is actually worse than a random walk model. In other words, a random walk model describes the data better than your model.